logical components are called gates. The gates can be used to simulate the logical operation. And so basically we have we can actually create a different actually circuit that defines different gates. And one of the gates is called AND gate. Okay. Sorry. Okay. And the NAND gate. Okay. So we actually talk about how to build the NAND gate first, using two actually switch, right? Use two switches, and then you can actually use three switches, two actually switches plus the one of the NOT gate to build the AND gate. Okay, so the NOT gate, okay, you can use just a one switch to build a NOT gate, and then you can build a NOR gate, OR gate. What else? There are a couple of different gates. So these NAND gates can be built using two switches, and two switches plus and you can use one switch to build a NOT gate. And so NAND gate plus the NOT gate, you can actually use these two gates to build an AND gate. And also you can use two switch to build a NOR gate. And then NOR gate plus NOT gate, you can build an OR gate. Okay. Now there's some other gates called exclusive OR. That's another gate. It's a very actually useful gate and widely used in the digital electronics. So these are the gates that we can actually build using the switches. And so you can use a various different notation to do this. And the AND gate can be described like this. This is the AND gate. Okay. This is the OR gate. Okay. So NOT gate can be actually draw like this. And NAND gate, it's basically the same as AND gate, but we put a small circle at the top. And also OR gate, that's all, or NOR gate, I'm sorry. That's NAND gate. And that's not. Okay. And also we described that we can use two AND gate to build an AND gate with 3 imports. Okay. So you can build a 3 import AND gate and a 3 import OR gate. Okay. So you can use two. You can actually check the presentation or check the handout material, so you can find out how to build this. Now, the good thing about this is that so you can actually, build the digital actually electronic circuits by using the logic, by using the Boolean expression. Okay, so you can find a relationship between Boolean expression and the electronic circuits. So we also discussed, what is the, what's the, how can I describe it? Oh, how can I actually simplify the Boolean expression? Now, so to answer the question, first we need to answer the questions like, what is the simplest form? Okay, and now, so we know that you can build many different actually Boolean algebra expressions, many different Boolean expressions with the same truth table. So that means you can build a different Boolean expression which basically perform the same functionality. So you can basically build the same truth table. So that says because you can find the equivalent, electronic circuit to simulate this Boolean expression. So that means that you can also build many different electronic circuits to perform the same functionality. Okay, so with the same number of input and with the same combination of input, like a 0, 1, 1, 0, the binary input, and then you can generate the same outputs. Okay, so we can actually build many different electronic circuits that performs basically the same functionality. Now, so then that comes a question like, what is the simplest, Boolean expression, or what is the simplest electronic circuit? Now, unfortunately, there's no general definition in terms of what is the simplest form of the logical expression or Boolean expression. Or so therefore, it's hard to say which, electronic circuit has a simplest form. But in practice, people can always, make some kind of judgment or use the common sense to figure out which form is the simpler form. Okay, even though there's no theoretical definition in terms of what is the simplest form. But in practice, we can always, find out the simpler form. The general rule of thumb is, if you can actually build many different logical digital, electronics device, the digital circuits, electronic circuits, then the electronic circuits with the fewest number of gates, with the smallest number of gates, that's the best, that's the simplest, electronic circuits. Now we talk about various different reasons. Why? Because, if you have fewer number of gates, then it's easier, the cost is going to be easier to build the circuits. Okay, it will be cost less to build the circuits, and also it's going to consume less power because, you have a fewer number of gates, therefore you have a fewer number of switches. Okay, so in modern days, when we talk about the various different digital circuits, we're talking about digital circuits with millions or thousands of millions or even billions of circuits, or billions of these switch or the gates inside these electronic circuits. Now, if you have a two design of the electronic circuits which perform exactly the same functionality, but one requires 3 million gates, the other one requires 2 million gates, and definitely, with the same functionality, the design with 2 million gates is definitely better than the 3 millions, right? With the 3 million gates, because the simpler the structure, number one, it's easy to manufacture. Number two, it consumes less power. Number three, it's less likely that the error going to happen because it's more reliable. The reliability is much better with a simpler structure. So that's basically the rule of thumb when we judge which, digital and electronic circuit is the better design. So in order to simplify the electronic circuits, typically the way we can do it is, first we need to actually convert. We can convert the electronic circuit into the logical or Boolean expression, and then we use all these, identities, the tables we just show, like all these, like associated law and distributive law and the various different actual laws to simplify these Boolean expression. Once you simplify the expression, then you can convert this simplified expression again back to the electronic circuits. Okay, that's basically the way to simplify the simplify a circuit. So here's the example we just talked about. Here's the Boolean expression, right? So the Boolean expression is here, and then we just say, can we simplify these? Now the electron circuit. Can we simplify this electronic circuit? Can we simplify the design? Then the first thing we can do is try to express using the Boolean expression. So here's the Boolean expression. So, and here's a step. Step one, we try to, in the first level, that the A and the B, and we get A asterisk B, and the B plus C. That's because that's the AND gate. That's OR gate. That's AND gate. That's OR gate. AND gate again. So then you have import A, import B. So you got output A times B. Import B, import C. You got B plus C. And the import C and the import B. You got B times C. Okay. And then, so B plus C and the B times C again go through the AND gate. So we go to our next level, right? So we actually get the B times C times B plus C. And then this combined with this using the AND OR gate, and you got the final result. Okay, so this is actually the final expression. So now the first thing we need to do is try to simplify these, Boolean expression. So here, I just provided one way of doing this. There are various different ways because you can apply various different Boolean identities. Okay, so this is just one way. So eventually, we can simplify this original Boolean expression into this. Okay, now first we got this B times A plus B times C. So you have B and A, B and C, then OR. You put the OR together. And then we can find out using distributive law, we can actually pull the B out. And so this way, you can reduce the number of operations. Because remember, each operation and or represent a gate. Okay, so this represent the AND gate, this represent the OR gate. Okay, so in that case, you have 3 gates, but here you only need 2 gates. Now, once you got this simplified form, then I can actually rebuild the circuit. So now, based on the precedence of these operations, now first the precedence is going to give to the parenthesis. If I have a parenthesis, A plus C, so the operation in the expression inside the parenthesis is going to be evaluated first. So A plus C, then we can actually build with the AND gate. Okay, A and C plus C. And then we just actually A plus C, and then there's another one B. So we can actually build this B times A plus C. So this is actually the logic, the electronic circuit, which basically perform the same functionality as this one. Okay. So it's much simpler, right? Because it used actually 5 gates, but with this, you just need 2 gates. So that's basically the simplification, how we're going to simplify the electronic circuits. And we also talk about this. How can I simplify this? And this is actually kind of stupid. You try to actually split the line and put this in the AND gate. Is there any questions? Is there any questions? Okay, so normally you don't do this. So I just take this one, just cross this one out because Okay, so the next thing I want to talk about is a special electronic circuit. Electronic circuit is called set reset flip flop. Okay, so we can define various different logic circuits to perform different functionality. Now, for most of the digital computer systems, all the components are basically built upon the electronic circuits. Okay, so the processors, the memories, the or any kind of components inside the computer system, it's actually built with the circuits. So a process is a circuit, and the memory is a circuit, and so now the flip-flop, set reset flip-flop, is a kind of electronic device that allow people to store data. Now, one actually set reset flip-flop allows you to store 1 bit. Okay, you can store 1 bit. So that means you can either store a 0 or store 1. It sounds actually not much, but it's okay because we can use the integrated circuit, right? Once you build a flip-flop, and then you can actually, combine 2 flip-flop, combine 3 flip-flop. So you can actually store, if you combine 8 flip-flop, you can store 8 bits, which is 1 byte. Okay, so now if you want to actually, build store one kilobyte, which you can actually build 1024 set. I'm sorry. We can use if actually build 1 kilobyte. One kilobytes, that means you need 1024 bytes, or 1024 times 8 bits, right? So just you need to actually, put together how many actually flip-flops. A lot, right? But that's okay, because the modern technology allow people to make the flip-flops extremely small, So you can actually basically put like millions or even thousands, 100,000s, or even billions of these gates or the switches in one circuit. So you put together, you can think about how many actually bytes you can store with integrated circuits. Okay. So let's talk about this. A flip-flop often referred as a latch. It's basically a term referring to an electronic circuit that have 2 stable states. Remember, it have 2 stable states. Remember, when you actually build a circuit with like a AND gate, you need 2 inputs, right? 2 inputs and 1 output. So then, in order to generate the output, you have to put the input value. So if it's an input 0, 0, because it's an AND gate, then you got a 0. And if you actually have a 0, 1, you also got a 0. And the 1, 0, you got a 0. And the only time when you actually have a 1, 1, then you got 1 out, right? So because this basically simulates some kind of AND operation. So, but in that case, the state of these either input or output, they're not stable, because the number 1 never going to stay, because it's dependent on the input. If you change the input, the output may change. So there's no way you can actually keep a data and store a data that way. So to make actually some kind of electron, a storage like a memory, you need a stable state. So that means once you actually store a data 0, so you're going to keep the 0 no matter what happens, no matter what the input you're going to change. The data stored in this device should actually stays that value. Never going to be able to change it. Okay, unless you really want to change the value. But once you changed it, then it's going to be a stable state again. So that's basically the basic requirement for a circuit that can be used as a storage. Let's take a look. Now here's the design. If you search to Google, you will find out you have actually various different ways to build the flip-flop, the set reset flip-flop. This is just one way. So the set reset, or sometimes we call RS or SR flip-flop, has two input actually wire. There are two output wire. Now the design, you can design like this. So you basically need two OR gates plus two NOT gates. Okay. Now the set and reset input are initially set to 0. Both set to 0. Okay. Now what is the actually value for Q here? Now here's a Q, and here's the negation of Q. So that means if the value of Q is 1, then this side is 0, or vice versa. So if this is 1, that's 0. So the number gonna actually switch between these two output. Now, how can we use this as a storage? Let's take a look. Okay. So remember, initially, both set and reset are set to be 0. Now, can you tell me if this is 0, this is 0, what is the value for Q? What is the value for Q? Or can we decide what is the output value, whether it's a Q or kill the Q?
Q is 1.
Can we decide what is the value of Q?
I think we cannot tell, I feel, because it's a deadlock, right? I mean, without Q input, we cannot solve the circuit.
Okay. So it's hard to say, right? You don't know. And I think I don't care because I'm going to use this as a storage. So I want to store a number. For example, I want to set a value Q to be 1. Okay. Once I set to 1, then you cannot change it unless you want to follow certain kind of rule to change it. Okay. Otherwise, you cannot change it. Okay. Now let's see how it goes, because you want to set a stable one. So let's say I want to store a number. Okay. Now, if I want to store a number here, for example, I want to store a number 1 in here. So if I have actually set a number 1, and this must be 0, okay? So how can I do this? Let's see. Let's take a look. Okay, let me actually first erase it. And let's start to work on this. Now to store a value. So if you want to store a value, so then you're going to actually change the set. Now here's reset. You change the set to 1. Okay. If I change the set to 1, now what happens? What is the output here? So the output is going to be determined by these two imports, right? And what is this import? This import is actually coming from the output of the second one. But if I set this value to 1, it really doesn't matter what is the value of this, right? Because this is OR gate. Now, what does OR gate means?
So if both zeros means 0, otherwise always 1.
Okay. In an OR gate, if one input is 1, the other input, I say X, I don't know, X could be 1, could be 0. It doesn't matter. The output is always going to be 1, right? That's
Yes.
OR gate. That's the
Yes.
OR gate. So this must be 1. Okay. If I set this input, the set input to 1, then the output is going to be 1. So if the output is going to be 1, and I'm going to pass through the NOT gate, so the output for the NOT gate is going to be
0.
0. Okay. Now remember, both sides are 0, right? So I only change this to 1, but this is still 0. Now, if the output here is 0, and then if you go all the way, this becomes the input for the AND gate on the lower AND gate. So this is going to be 0 as well, right?
Yes.
So this is 0 already. This is 0. Once I set to 1, this becomes 1, this becomes 0, and this becomes 0. And now you got a 0, 0, and then output is going to be
0.
0, because that's all set. And that's
1.
1. Okay. Now, once you set this, okay, now I'm just done. So when I actually set, put the value set to 1, and then I immediately change this value back to 0. Okay. And then once I change this back to 0, I actually, two input are going to be 0 and 0 again, right? Once I actually change back to 0, what is the output?
Stays the same.
Stays the same, right? Because if I change back to 0, here's the 0, and then this side is 1 because it's connected to the output here, right? So this is 1. 1, 0, even though this becomes 0, and here's a 1. So a 0, 1, because it's OR, so it's still 1. So it's still 0. Okay? So then down here, it's still 0, and it's still 0, 0, and still 1. Okay? So it's kind of like some kind of a loop that you can actually eventually, even though you set this, you change the value of the set to 0 again, so it doesn't change the output. So that means if I change 0, 1, if I actually change the value of set, it doesn't change the output. So this output is a very stable value. Okay. So I basically store a bit, which is 1. Okay. Or if you count this top, you can say I store a 0, but you only store 1 bit because these two are always opposite. So you can only store 1 state. So basically I can say I store a value 1 because, when I reset to 0, it's 1. So if I even actually change this one back to 1, it doesn't change the output. Okay. Okay, so this way I store a value to 1. Now, so this is actually what happens. So I have both set and reset to 0, and I change the set to 1. So, and then this becomes, if I change this set to 1, then I got a 1 here. Okay, next one. So I got a 0 here. So this makes that part is also 0. And then this is 0 plus 0. I got a 0 here. Okay. So eventually I got this. Okay, so once I reset, change the value of set back to 0, and that value is still going to be 1. So it's a kind of stable value. Okay, now, so this is actually how I'm going to set the value to 1. Okay, so then I change the set and both the set and reset back to 0. Okay, so then that value going to stay, no matter what happens, it's going to stay. But if I want to say, what about if I want to store a 0?
We need to make reset 1.
Okay, then you can do the opposite. You can change this value to 1, right? Suppose that currently I store 1, okay? So if I don't change both, then it's going to stay as a 1. But if I change this to 1, so they're going to make this 1, right? Even though this one's 0, but this is going to make this becomes 1. If this is 1, then this false the value, the output becomes 0 because that's a NOT gate. And this is going to be 0 here. And the 0, 0, I got a 0, I got a 1 here. And then once I actually successfully set the Q to 0, I'm going to actually change this value back to 0. If I change back to 0, it doesn't change the result because this is 1. So this one changed to 1. Even I change this one back to 0, then it's still actually 1. And this is still 0. So then I got a stable state, stable value of 0. So this is basically, so if you, so in order to stay a number 1, you change, initially you have to assume that you have to you have to actually set both the set and reset value to 0. So set and reset has to be 0. Okay, and then if you want to store 1, change the set to 1 and change back to 0. So this is going to store 1, store a value, store a bit 1. Now, if you want to switch, change the value to 0, then you change this actual reset, change the reset from 0 to 1 and change back to 0. And this way, you actually change the output, actually change the value to be stored in the flip-flop. So the Q going to be actually becomes 0. And this going to be also stays as 0. As far as you don't change the set, you're going to stay as a 0. So to store the number, you need to actually work on both the set and reset. Okay. Does it make sense?
Yes. Yes.
Okay. So that's the set and reset flip flop, and it's pretty simple. You can store 1 bit. Okay. Now, if you want to store 2 bits, then you just combine 2 flip flops, and if you have a million flip flop, you can store 1,000,000 bits, and 8 million bits going to be 8 million bytes. So it's a pretty big storage space. Okay. Because 1,000,000 flip flop is not really that many, because you can make the electronic circuit extremely small that you can put so many gates, you can put so many switches in there, then you can make the storage extremely big. Okay. This is just one technology people use to store the data. Okay. Okay, so here's one more example. I'm not going to talk about this example in the class, but if you want to work on this, you can actually just check the PowerPoint, and I published on the Blackboard, so you can actually take a look. So you have a 3 input A, B, and a C. So you can actually simplify these with 3 inputs and 5 gates. Okay. 1 AND gate, 1 NOT gate, actually 1 NOT gate, 1 NAND gate, 1 NOR gate. Oh, actually 2 NAND gate, 2 NOR gates, right? So you have 2 NOR gates. That's NOR gate. That's an OR NOR gate. That's NAND gate. And that's AND gate. And this is NOT gate. Okay. So how can you simplify this? Then you need to actually figure out. So here's A, here's a B. So okay. So B and a C. So you got a B and a C, right? That's the output here. And then NOR gate here. Okay. So what is it? You can actually figure out what is the. So it's actually A plus B times C. Not, right? Something like this. And you can do the same thing. So that input is actually B. Okay. So basically, if I use the curve, that means this line past this line and never intercepted to each other. If I actually say intercepted, then I need to actually put the small dot circle over here. So that means this is A. Okay. This is the same as A, and this is same as B, right? Yeah, this is same as B. So this is not B, and A times not B, and not again. So something like this, and then you can actually say here this is here, and then NOR gate again. So somehow you need to figure out, how to simplify these things. Okay. I think that's pretty much all for the module 3. So okay, before I actually move forward, do you have any questions? Okay, so that's pretty much the topics for the Boolean logics and the Boolean algebra, and how you actually apply the Boolean logics and Boolean algebra to in the electronic circuit design. So even that's just introduction. So I'm not actually talking about any sophisticated actually logic, the circuit design. That's a lot, because if you want to actually design a processor, or if you want to design a processor is just a, so in the computer architecture class, you actually doing the job of design a processor. So a processor is just a logic circuits that have a whole bunch of imports, that with the combination of this import, then you can actually generate output. Now, depend on what kind of combination you have, it's just form different instructions, right? If each instruction gonna actually generate certain output, another instruction with another actually binary sequence, then you're gonna generate another output. So based on this, you can design a processor, and then you can design a memory. Then you can actually put the processor memory together, then you can build a small computer, So the computer architecture course or computer organization course can allows you to build a small computer using some kind of a software, But this course, I'm not going to spend much time this, but just give you some kind of introduction in terms of the Boolean algebra and how we can apply this Boolean algebra into the design of electronic circuits. Just build a relationship between these two. Okay, so I think it's probably a good time to have a small break before I start the module 4.
Professor Chen?
Yes?
I had a little doubt regarding the flip-flop diagram. Is it always represented the way you showed, or can we use 2 NOR gates instead of 2 OR gates and 2 NOT gates?
Yeah, you can always find a different way to design these circuits, because as far as we know that you can always find a different logical actual design which actually perform the same functionality. You can build a same truth table for that, for various different logical design. Yes, you can. This is not the unique. There's no unique way to build a particular logic in a logical. You can have many different ways to do that. I think if you search Google, you can find many different actually set reset flip flop design. This is one of these. It's not unique.
Okay,
Yes.
thank you.
Okay, so I think it's a good time to have a small break, because we're gonna change the topic afterwards. Let me actually stop the recording. Normally